instabilities which will probably destroy the nature of the curved black holes in the area. So all bets are off. It's probably, the singularity may be rather different from the structural case, but probably not that different. One expects to find, well, if you believe the least speed of the this analysis, you'll have very complicated oscillations in the bar curvature and rapid divergence. And that will happen whether it's curve or whether it's rotating or not.
Paul, on these. So, Roger, you've got an overall arrow time running from eon to eon in the same direction, which is outside the scope of what you've been talking about. That would be something that would be at a deeper level. Is that right?
Yes.
And then the second question is, you look like you're sort of playing fast and loose with the non-conformal degrees of freedom. You sort of shrugged it aside and said that Paul Todd had provided the transformation. But can you say a little bit about why we can just ignore all that?
I should say that you can't completely ignore it. And in particular, I haven't said anything about electrons. It's hard to get rid of them all. There will be a row of electrons running around, and they, according to current physics, they will still be there right at the very remote future. So that you can't get rid of the non-conformal degrees of freedom if that's right. But in order for this scheme to make sense, I really want to get rid of them. Which means, probably, although various crazy thoughts one can have on this, but the least crazy is that there is a general tendency within one eon, a general tendency for mass to decay away, so that the electrons would ultimately become massless. But they would only do this at the final boundary to become actually. Now that's an unconventional picture. It's the thing I worry about most in this scheme, if you like, apart from being shot down by observations, which is that charged particles, we don't have charged massless particles now, and we can't have, there will be problems with pair annihilation and so on and so on. So there's nothing against the particles becoming ultimately massless. Now, you see, one thing about present-day particle physics is that we haven't the remotest idea why particles have the masses that they have. And so this means we haven't the remotest idea why they have some particular value in terms of Planck masses. And so we certainly haven't any theory which tells us that they should not reduce by comparison with the Planck mass as time goes on. So this scheme would say that would have to happen, maybe extraordinarily slowly, but this is the picture that I have. So that those degrees of freedom will finally disappear, and that in the Big Bang, the high temperature, and maybe Higgs mechanisms and what have you, the high temperature will tell us that we have massless ingredients at the beginning. And then the last thing that I was trying to say rather rapidly is that there's a sort of transformation where you could go from a vacuum with no matter in it to, with a big conformal transformation, to lots and lots of matter, which I'm interpreting as dark matter. So there's a kind of invariance that enables you to go, once the massive entities have gone, you have this extra freedom, which means the universe is able to recalibrate itself in this way. Of course, why doesn't it go the other way? And is there a theory which governs how fast it does it? All sorts of things. There ought to be. I don't know what it is. So the proposal here is clearly lacking in underpinnings of that sort. But that's the proposal as it exists now.
How might this fit in with the inflation theory and the symmetry breaking due to the Higgs field?
Yes, thank you for that comment. Particularly the inflation comment, because I didn't mention inflation apart from, well, I think, the transparency. This scheme doesn't have any inflation in it. It's an alternative to inflation. And you do get, well, see, what's the evidence in favor of inflation? Well, there are various arguments which aren't really, let's ignore some of them. The main arguments in favor of inflation are the observational ones that, first of all, there are correlations between distant regions in the microwave background, which in the standard cosmological models would be outside each other's horizons. And so how could they be correlated if they were never in communication? In inflation puts this earlier phase in, which brings in the communication. In this scheme, you don't need that, because the correlations come about through the black hole encounters in the previous eon. In the inflation view, the fluctuations in the microwave background come about from quantum fluctuations in the early universe, expanded out by the inflation. Here, it's much more classical. In certain respects, although this is wild, it's also rather conservative. Because you might say, what's quantum gravity doing here? Well, it's almost a classical theory. The theory is completely smooth. It's saying the universe is completely smooth in the conformal geometry. Okay, the scale factor is something funny, but the conformal geometry is completely smooth in this picture. And the correlations between distant points in the background come from the previous eon. Now, you also need the other main support of inflation is the scalar variance that one sees in the fluctuations. And my view is that that does seem to happen here too. That needs more looking at. I'm not totally sure about that. But it seems to come about because there is an effect of inflation which occurred prior to the Big Bang. And that is the exponential expansion that took place because of the cosmological constant. You have this exponentially expanding universe in the previous eon. And so I think that would lead to something like the scalar variance that one sees. I'm not sure about that, so it could be shot down on that too if that turns out to be wrong. What about Higgs fields? Well, I'm using something a bit like that. I'm saying in the early universe, according to the standard ideas in particle physics, mass comes about through this Higgs field. And that would only start to operate when the energies get lower than that of the Higgs particle. Once you go prior to that, things are effectively massless, which is consistent with the scheme I'm saying here. But in the very early universe, particles are massless, and it's later on that they acquire mass. So it's consistent with that kind of thing. It may be that it's something a bit different from that, but that's fine by me.
I may be getting misled by your picture up here, but it looks like what you're saying is that the Big Bang is not necessarily starting from a point in our universe. It looks so it's spread out somehow. Or if it does start from a point, you said earlier that the universe is accelerating in its expansion. So how do you make the smooth transition from an infinitely spread out universe to going back to a point? Or does it not start at a point?
Well, first of all, the point, long before any of the things I'm saying here, the singularity has been analysed from the conformal point of view. And from the conformal point of view, it's not a point, which has to do with the horizons. The fact that you introduce the conformal rescaling and it does stretch out. This is nothing to do with my particular perspective that I'm presenting today. It's just what happens if you look at the standard models. If you look at the standard models with or without inflation, you find that the Big Bang is causally a space-like surface. So that stretching out is not an unconventional thing I'm saying here. It's just an analysis of the causal structure of all those models. What I'm saying is not just that, it's a real thing. And that the stretching out is something that the universe is insensitive to. That the causal structure, the conformal structure, those parts of physics which don't have rest mass in it, that are insensitive to that stretching. But the stretching expresses much more neatly the causal relation between things at the Big Bang. And then I'm saying, well, I'm matching them, that's less conventional. What is perfectly conventional is the stretching out to make it look like a space-like surface. What's less conventional or unconventional is to say that is to be identified with the remote future of some other eon. Now that's the wild situation.
Yes. You showed pictures of photons being curved, being bent by gravity, and pictures of lensing effects.
Yes.
Well, in a lens, the reason that light refracts is because the wave speed decreases toward the inside of the curve. And in fact, if the light speed is changing as you approach a black hole, the light is going to slow down, and we're going to get an inflation